Sometime in the late spring of 2024, without any warning, without any telescope catching it happen, something slammed into the surface of the moon with enough force to release energy equivalent to hundreds of tons of TNT. Nobody saw it hit. Nobody heard it. The moon has no atmosphere to carry a shockwave, no witnesses close enough to notice. The only reason we know it happened at all is because a spacecraft orbiting far above quietly photographed the same patch of lunar surface, months apart. And when scientists compared the two images side by side, they found a hole in the ground that had not been there before, 225 meters wide. More than 3 times larger than anything NASA's Lunar Reconnaissance Orbiter had documented, forming during its entire 15-plus years in space. This is the story of that impact, what it reveals about a moon that never actually stops changing, and why scientists are now calling it a genuinely rare, once-in-a-century kind of event. To understand why this discovery matters, you first have to understand something most people don't think about when they look up at a full moon. What you're seeing isn't a fixed, finished object. It's an active record, still being written. Every dark patch you can pick out with your naked eye is an ancient impact basin, blasted open by a collision so massive it reshaped an entire region of the lunar surface. Every crater crowding the lighter highlands is the frozen signature of another impact, sometimes billions of years old. But unlike Earth, the moon has no atmosphere to burn up incoming debris before it reaches the ground, no winter rain to smooth over the damage afterward, no plate tectonics to erase old scars and replace them with fresh terrain. Whatever hits the moon stays exactly where it landed permanently, and new impacts are happening on its unprotected surface constantly, right now, every single day, in sizes ranging from microscopic dust grains to boulders large enough to leave a lasting mark. That's precisely why NASA has kept the Lunar Reconnaissance Orbiter, or LRO, circling the moon since 2009, methodically photographing its surface again and again over the years. One of the mission's ongoing jobs is exactly this kind of before and after comparison, taking new images of previously photographed regions and checking for anything that's changed. A scar that wasn't there the last time the spacecraft passed overhead. It's slow, patient, unglamorous work, the kind of long-term monitoring effort that rarely makes headlines on its own, precisely because most of the time it turns up small, modest craters, unremarkable evidence of routine bombardment that the moon experiences constantly and has for billions of years. Before this particular discovery, the largest crater LRO had documented actually forming during its entire mission was about 70 meters across, itself already a genuinely uncommon find given how rare large impacts actually are. Then came this one. Using LRO's camera system, a research team led by Mark Robinson at Arizona State University compared images of a specific patch of lunar terrain taken before and after the impact occurred sometime in the late spring of 2024, and the difference was unmistakable. A fresh crater, 225 meters across, roughly the combined length of 2 football pitches laid end to end, had appeared where nothing had been before. It wasn't just the width that stood out. Inside the crater, researchers identified patches of unusually dark material, evidence that's become something of a signature for genuinely violent impacts. That dark coloring is glassy rock, flash melted almost instantaneously by the colossal heat generated in the collision, then just as quickly resolidified into a hardened glass-like surface, a kind of fingerprint left behind specifically by impacts energetic enough to briefly liquefy solid rock on contact, releasing an amount of energy that dwarfs anything a research team could safely or ethically recreate in a laboratory setting. Mapping the crater's interior in detail, the team traced out its elevation profile and found it had carved a genuine funnel shape into the lunar surface, a clean, deep depression consistent with an object striking at extraordinary velocity, likely tens of thousands of kilometers per hour, the kind of speed typical for a stray asteroid fragment or piece of comet debris intersecting the moon's orbit. Based on established models of how frequently impacts of this particular scale actually occur anywhere on the moon's surface, researchers describe an event like this as something that happens, on average, only around once every 100 years, for any single new crater of this specific size to form. That's the number worth sitting with. Not once every 100 years across the moon's entire multi-billion-year history in some abstract geological sense. Once every 100 years as an ongoing statistically expected rate right now in the present era, which means LRO essentially caught a genuinely rare, actively occurring event red-handed, purely because its cameras happened to be watching the right patch of ground at the right 2 moments in time, a matter of pure observational luck layered on top of years of methodical, deliberate monitoring effort. It's worth understanding just how significant that kind of catch actually is in the broader context of lunar science. For most of human history, our entire understanding of lunar cratering came from studying craters that were already ancient by the time we found them, sometimes billions of years old, their original formation completely unobserved, reconstructed only indirectly through geological analysis of rock samples and crater morphology, extrapolating backward from a finished result to guess at the violence that originally produced it. LRO's ongoing before and after imaging campaign flips that completely. It lets scientists study a crater's formation essentially in real time, comparing the pristine, freshly excavated state of an impact site against a known baseline image of the exact same terrain from before it happened. That gives researchers something genuinely rare, a controlled, dated data point for exactly how much energy a specific sized impact releases, exactly what the resulting crater's shape and depth actually look like immediately afterward, and exactly how quickly or slowly weathering processes like micrometeorite bombardment and thermal cycling begin to soften the crater's sharp edges over the years that follow. Information that simply cannot be reconstructed after the fact from an ancient crater alone, no matter how carefully it's studied. This isn't an isolated case either. NASA's broader lunar monitoring efforts have documented other, smaller fresh impacts using the exact same before and after methodology throughout 2025 and into 2026, including a comparatively modest 22-meter wide crater identified earlier this year by comparing sequential orbital images of the same terrain. Individually, discoveries like that smaller crater barely make headlines, quiet, routine confirmations of a bombardment process that's been ongoing since the moon first formed. But taken together with a 2 to 25 meter crater from 2024, they paint a consistent, increasingly well-documented picture. The moon is not the static, unchanging backdrop most of us grew up assuming it was. It's an actively evolving surface, its geology still being written in real time, one impact at a time. And thanks to consistent, patient orbital monitoring, we're now catching more of those individual moments of change than at any previous point in the history of lunar science. That picture of an actively changing moon isn't limited to fresh surface impacts either. Other recent lunar research has been quietly reshaping our understanding of the moon's deeper structure and history, adding further weight to the idea that this world still has genuine surprises left to reveal, even after more than half a century of close study. Scientists working with rare rock samples returned by China's Chang'e 6 mission, which retrieved material directly from the moon's far side, have found evidence suggesting a colossal ancient impact reshaped the moon's interior far more deeply than previously realized, altering not just the surface, but the underlying structure of the lunar mantle itself. Separately, two companion studies focused on the South Pole Aitken Basin, an enormous ancient impact structure on the moon's far side and one of its oldest surviving features, found that regions surrounding that basin contain rocks that originated deep within the lunar mantle, material effectively excavated from far below the surface by the sheer violence of that original ancient impact. Researchers involved in that work have noted this could give future Artemis astronauts exploring near the lunar South Pole the rare opportunity to physically walk across and directly sample rock that originated from deep inside the moon, material that would otherwise be completely inaccessible without drilling far deeper than any current mission is capable of. There's a broader scientific context making all of this monitoring especially urgent right now, and it connects directly to NASA's renewed human exploration plans. In April of 2026, 4 astronauts completed the Artemis II mission, the first crewed journey back toward the moon since the original Apollo program ended in 1972, spending 10 days aboard a lunar spacecraft and becoming the first human beings to view the moon's far side without the assistance of a telescope, a genuinely historic milestone in its own right, one that also returned unexpected new findings about the moon simply from having human eyes and instruments in that specific vantage point for the first time in over 50 years. NASA is now actively preparing for the follow-up mission, Artemis III, planned for 2027, which is expected to include the first crewed lunar landing in over half a century, and current planning already includes an unusually ambitious orbital rehearsal in which Orion astronauts will practice separate rendezvous and docking maneuvers specifically to prepare for the complexity of that eventual landing attempt. Understanding exactly how frequently and how violently fresh impacts continue striking the lunar surface isn't simply an academic curiosity in that context. It's a direct, practical safety consideration for any future astronauts or any permanent lunar infrastructure that NASA hopes to establish there. Just this month, in July of 2026, NASA awarded nearly $600 million across 4 separate commercial missions specifically aimed at building toward a permanent lunar base, planned for late 2028, alongside a separate round of funding for 41 additional commercial space technologies covering everything from lunar power generation to protecting spacecraft and equipment from the moon's notoriously abrasive dust, a persistent, genuinely difficult engineering challenge, given how sharp and electrostatically clingy lunar regolith actually is. Each of those newly funded lunar landing missions is expected to carry the same trio of science instruments, specifically chosen to improve lunar navigation and to study exactly how dangerous that surface dust becomes when disturbed by landing spacecraft or walking astronauts. Every one of those future missions and installations will exist inside an environment where a 200-plus meter crater can appear without warning, roughly once a century, and where far smaller impacts are happening on a genuinely continuous, ongoing basis. That safety consideration is about to get an unusually direct, real-world test case of its own. On August 5th, 2026, just days away as this story is being told, an abandoned upper stage from a SpaceX Falcon 9 rocket, originally launched back in January of 2025, carrying 2 private robotic lunar landers, is predicted to crash into the moon's surface near a location called Einstein Crater. Unlike the naturally occurring 2024 impact, this collision is fully anticipated, tracked, and predicted well in advance, giving astronomers a genuinely rare opportunity, the chance to observe an artificial impact happening in real time, rather than discovering the evidence of a natural one only after the fact through before and after image comparison. A research paper recently published on the ArcSciv preprint server, led by researcher Benjamin Fernando, has specifically called on both professional and amateur astronomers around the world to observe the event as it happens, hoping to test new methods for precisely pinpointing exactly where an object strikes the lunar surface. Techniques that could prove directly useful for future lunar seismic experiments designed to study the moon's internal structure using exactly this kind of impact-generated shockwave, essentially turning a piece of abandoned space junk into an unplanned but genuinely valuable scientific instrument. Taken together, these threads, the naturally occurring 2 and 25-meter mystery impact discovered from 2024, the deep mantle insights emerging from Chang A6 samples and South Pole Aitken Basin research, and the fully predicted, deliberately observed rocket stage impact arriving just days from now, represent different facets of the exact same ongoing scientific effort. Understanding, in as much precise, real-time detail as possible, exactly how the moon's surface and interior continue to be shaped by impacts, whether ancient or fresh, natural or artificial, large or small, expected or completely unannounced. Every one of those data points adds to a growing, increasingly detailed picture of a surface that most people assume is simply finished, frozen, complete, when the evidence increasingly suggests something closer to the opposite. The moon is still being sculpted, one collision at a time, and thanks to a spacecraft that has spent over a decade and a half patiently, methodically photographing the exact same stretches of ground again and again, we are catching more of that ongoing sculpting in the act than any previous generation of scientists ever managed to. What makes a story like this genuinely worth pausing on isn't shock value or exaggeration. It's the quiet, factual strangeness of the moon's real, ongoing nature. A surface most of us have looked at our entire lives, assumed was static, ancient, essentially unchanging, is in fact still being rewritten, sometimes violently, sometimes without any warning at all. And increasingly, thanks to careful, sustained orbital monitoring, we are finally in a position to actually witness it happening, rather than simply studying the aftermath centuries or millennia after the fact. And with human astronauts scheduled to return to that same unpredictable surface within the next couple of years, understanding exactly how often and how forcefully the moon still gets struck has stopped being a matter of pure scientific curiosity and started becoming a genuinely practical question with real consequences for the people who will eventually be standing on that ground.